In the previous video, we talked about even and odd functions, and now we're going to look at some properties of even and odd functions in integration. So the theorem is, well, there are two parts. So in this theorem, f is an integrable function. Okay, so if f is an integrable function and it's even, I'm just going to put integrable in parentheses because I'm going to talk about the integral. So if the function doesn't have an integral, then of course what I'm saying doesn't make sense. So if you have a function that's even and the integral exists on the closed interval from, say, negative a to a, then the integral from negative a to a is 2 times the integral from 0 to a. So that's if f is even, and if f is odd, again, integrable function, then on the interval from negative a to a, then the integral from negative a to a is 0. Let's draw some pictures just to illustrate why this is very plausible. So if you have an even function, why not just look at x squared for an example of an even function? So this is an even function. What I'm saying is that if you want to integrate from negative a to a, you can just do the integral from 0 to a and then multiply that by 2. Well, why does that make sense? Well, we think of the integral as the area under the curve, right? So what this fact is saying is that the area from negative a to 0 is the same as the integral from 0 to a. It's the area, these two have the same area. So if you wanted to find the total area from negative a to a, you could just find the area from 0 to a and then multiply that by 2. And that'll give you the area from negative a to a. So that's where we're using the fact that f is an even function, that it has this symmetry about the y-axis. So this is even. And what about if f is odd? So a good example would be f of x equals x. If you look at f of x equals x, okay, and you integrate from negative a to a, do you see what's going to happen? So this area, you're looking at the area under the curve, but in this case, it's actually above the curve for this part to the left because the curve is below the x-axis. But the area here is negative, and it's going to cancel with the area on the right, which is positive. And the idea is that these two regions, these two triangles, have the same area because the function has this 180-degree symmetry. Right? So the areas cancel out, and then you would get 0. That's the idea. So that's why it makes sense that this theorem is true. It's very believable. There's nothing surprising about this theorem, basically. So let's actually look at a proof. So what I gave above is sort of like a geometric reasoning that explains why it would make sense if you think about the area. The integral is the area under the curve. But let's look at an algebraic way of being sure that this is in fact true. So for part A, we want to look at the integral from negative a to a. And we can split that up into the integral from 0 to a plus the integral from, the integral from negative a to 0 plus the integral from 0 to a. And then the idea is to use a u substitution, so you let u equal negative x. Okay, then x is going to be negative u, right? So dx is negative du. So when we do a u substitution and apply it to this integral from negative a to 0, okay, so we use the substitution, x is negative u, so f of x is going to turn into f of negative u, dx is going to turn into negative du. Negative a and 0, right, we have to change those bounds also to the bounds of u. So when x is negative a, then u is equal to a. When x is equal to 0, u is equal to 0. So this is what you get after doing the substitution. So now I have an integral from a to 0. Let's switch it to an integral from 0 to a. Well, when you switch it to an integral from 0 to a, the minus sign, you have to multiply by negative 1. So this minus sign is going to go away. That's in front of... This minus sign here is going to go away when you switch the order of integration. Okay, and then you get f of negative u. Now f of negative u is just, if f is even, this is just f of u, right? So that's because f is even. Now the integral from 0 to a of f of u du is just equal to the integral from 0 to a of f of x dx. Because we're just using a variable, right? I mean, if you integrate t squared from 0 to a, you get the same as when you integrate x squared from 0 to a, or v squared, or w squared, or z squared, or whatever. It doesn't actually matter what the variable is called, right? So it doesn't matter whether your variable is u or x or whatever, you're going to get the same result. Okay. So the integral from negative a to 0 is the same as the integral from 0 to a, right? So therefore, okay, if you look back at what we have the integral from negative a to 0 plus the integral from 0 to a. Now, we know that this is just equal to that. So you're just going to get 2 times the integral from 0 to a. Because you have the integral from 0 to a plus the integral from 0 to a. That's just 2 times the integral from 0 to a. Okay, so that was part A. Now let's look at part B. So we have to evaluate the integral from negative a to a. Again, we'll use the u substitution, u equals negative x. Okay. Then, if you look at the integral from negative a to a, this is going to switch into, we're going to use the bounds, we're going to switch the bounds, right? Negative a is going to turn into a is going to turn into negative a, dx is negative du, right? So you have a minus du, and then f of x is f of negative u, because u equals negative x tells you that x is negative u. Okay, now we're given that f is odd, right? So since f is odd, f of negative u is equal to negative f of u. That's because f is odd. So f of negative u is negative f of u. Now the minus signs cancel, so this is the integral from a to negative a of f of u du. Right? Because I'm just doing negative 1 times negative 1 is positive 1. I can pull this negative 1 out of the integral, and then I get negative 1 times negative 1 is 1. Okay, finally, I can rewrite this as the integral of f of x dx for the same reason as before, that it doesn't matter what letter I use for the independent variable when I'm doing a definite integral. And then the last step is to change the bounds, to reverse the bounds of integration. So I'm going to get a minus integral from negative a to a. So what did we do? Okay, we've shown that this integral from negative a to a of f is equal to minus the integral from negative a to a. So since the integral from negative a to a is equal to minus itself, okay, what is the only number, okay, that is equal to minus itself? 0, right? So since these two are equal, it follows that the integral from negative a to a is 0, which confirms what we would expect to be true. Or if you don't follow the reasoning that the only number that is equal to minus itself is 0, I mean, another thing you could do is just add the integral from negative a to both sides. So you get 2 times the integral. Right, so you get 2 times the integral from negative a to a is 0, just by adding the integral from negative a to both sides, and then you divide by 2, so then you get 0. That's another way of seeing it. But I think it's a little easier to just observe that you have a number is negative itself. And the only way that can happen is if the number is 0. Okay, so that is a basic property of even and odd functions. So for example, let's say you wanted to evaluate the integral from negative 6 pi to 6 pi of sine cubed 4x dx. Well, if you wanted to use the fundamental theorem of calculus, hold on, let me make sure. Oh, that's too tricky. Do I want a 3 or do I want a 4 even number? Let me think. Yeah, I think I want like a even number, so maybe sine to the 10th power of 4x dx. Well, we don't know the integral of sine to the 10th, right? So if you wanted to use the fundamental theorem of calculus, that would be very difficult. But notice that if you take this function f of x, okay, if you plug in oh wait, no, sorry, I don't want an even power, I want an odd power, like 9. Okay, if you tried something like this, if you plugged in negative x, you get sine to the 9th of negative 4x. So this is sine of negative 4x times itself 9 times, right? Now sine is an odd function, so this is going to be negative sine of 4x times itself 9 times. Right? I have 9 of these negative sine 4x's, so I'm going to get negative 1 times sine of 4x to the 9th power. So this is negative f of x. Right? So f is an odd function. So then the integral is 0. So that's kind of a nice thing to know. Of course, this only works when you're integrating from negative a to a. So if you wanted to integrate from negative 5 pi to 6 pi, then you wouldn't be able to do it. So this is a very limited kind of trick, but it's useful to know. Okay, do we understand why sine to the 9th power of 4x is an odd function? Because if you plug in negative x, okay, you get sine to the 9th of negative 4x. So that's 9 sine negative 4x is being multiplied by itself, and then sine of negative 4x is negative sine 4x because sine is an odd function. And then you have negative 9 negatives being multiplied, so you get negative 1. So that's why you have to raise this to an odd power. So if I had sine of 4x to the 10th power, then this trick wouldn't work, right? Okay.